All right, guys. So let me share my screen. All right. So we're just gonna do some revision work. Today's not a regular class day. We're just gonna do some revision work. So I might have a few students joining from Tobago who they were in my advanced program last year when we had a revision. So my daughter reached out to me, and so they are invited to participate in this session. All right. So we want to look at a couple induction questions first, and then you guys can tell me what other questions. And it is much easier if you tell me specifically which question you want me to do, because now it's not a matter of teaching over these things from scratch. But while I'm doing the questions, I'll give as much explanation to the process as possible. All right. So right now, we want to be doing, let me go back from this. We want to be doing mathematical induction. All right. And this is a method-centered topic. You know, there's a method. The method that you use to do the mathematical proof is based on the type that you're doing. Right? I just Brianna joined a while ago. Brianna. So we're just doing some revision work. So right now we're starting with a couple of pure maths topics, but if you have one or two advanced topics, that will be fine. Especially if there are topics that are also under pure maths. Right? So it's just a random revision class. Wasn't scheduled or anything like that. All right, so we're gonna start out with this mathematical induction. This is not an admaths, yeah, Brianna? This is not an admaths. This is a straight pure maths topic. And this is what we call the divisibility type. All right, this is what we call the divisibility type, and you have to know the method that you use for the divisibility type of mathematical proof versus the summation type. There's a difference. All right, and you basically use the same approach for all of them. I'll show you the key steps though. All right, so it's a mathematical proof, and there are certain key steps that you want to do. So we're doing that question that I've circled. Use mathematical induction to prove that this expression is divisible by 2. Fairly simple. So if it is divisible by 2, if this expression is divisible by 2, then it means that it can be expressed as 2 times some integer. All right? Because when it is divisible, it means that it is evenly divisible. So it can be expressed as 2 times some integer. So we normally start out that way to write a statement, right? Representative of this, which is to say, let, we'll call the statement Pn, be such that this is Pn. Let the statement be Pn. So we can reference this statement. Let the statement Pn be such that the 5 to the n plus 3 is equal to 2 times some quotient. And you're going to have to divide that quotient now. Or 2 times some other multiple, 2 times some variable, some value x, where x is an integer. And most times x is a natural number as well. But we can say x is an integer because it can become useful in the next part. And n is your natural number. All the time, n is a natural number. I don't need to set it in the question. I see there, n is a natural number. All right. So that is always the case. But if it is divisible by 2, this expression, then it can be expressed as 2 times some number that's an integer. All right. This is all going to be positive because this is positive. The natural number is positive, and this is a plus. So naturally, the x also is going to be positive. So if you wanted, you could have said x is also a natural number. All right. Well, let's continue. So how the process works is that you prove that it is true for n equals 1. So for n equals 1, that is your first step in the proof. Show that it is true for n equals 1. So for n equals 1, you basically substitute the 1 in there and show that it is equal to 2 times something. Right? 2 times something. So you plug the 1 in there, you get 5 to the 1 plus 3. This actually works out to be 8. And 8 is the same as 2 times 4. So I've shown it to be true because 4 is an integer. So basically we can say P1 is true. It is true for n equals 1. So P1 is true. So we can make that conclusion here and say P1 is true. That's the first step. P1 is true. So the statement is true for n equals 1. The next step is to assume it is true for some value k. That's just a process. Next step is to set up when it is true for n equals k. And since k is an n value, means that the k naturally then is an integer because n are integers. All right. So for n equals k, and this part is fairly simple. So you're gonna put the k up here, but then I don't have to call the quotient x anymore. I'm gonna call it q. That's my standard way of doing it. So for n equals k, this statement becomes 5 to the k plus 3 is equal to 2q. And the q again is an integer. So the q is going to be an integer. So the q now is built like an x value. And the n is still a natural number from here. So that has not changed. And right now, what we're saying here, what we're basically saying here is that pk is true. But the important thing is that in proving the third step, you have to use this result to prove the next step. That's what we call the induction phase. You have to induce this result in the next step. The next step is to prove that it is true for n equals k plus 1. So we're going to start. This is step 3, and this is usually the working step. Step 3 is the working step, is where the work takes place in this question. All right. So it is for n equals k plus 1. You have to be careful now. What it is that when you put in n equals k plus 1, you're going to put the k plus 1 inside this expression. Right? You're looking to use this inside that expression. So you have to be careful now. So I'm going to plug this in here. We don't write anything yet. So we're going to write 5 to the k plus 1 plus 3. But this is this important step now. Don't go writing the set equal 2 times nothing. No, you don't do that here, sir. No, you don't do that there. Right? What you're seeking to do is induce this result in this expression. And it must still work out to be 2 times something when you're done. So what you normally do then, when you write this expression, you work on this expression. You work on that expression, trying to extract, for example, 5 out of k from that one. Now, a hint I would do for this question, right, is to take this and make 5 to the k the subject, so I can substitute it in there. So from this expression, I could maybe go and write that 5 to the k would actually be equal to 2q minus 3. And so I can substitute this for a 5 to the k somewhere down there. But first thing you want to do is break the 5 to the k out of this, therefore. So what would this be equal to? And that's, remember now, guys, when you write this step, don't continue to write no 2q, nothing or anything like that. This is what must equal 2 times something, and you must use this in here. And I'm saying it is better to use what the 5 to the k is in this expression. So I'm going to break this up to get the 5 to the k out of it. So this expression right now is actually equal to 5 times 5 to the k plus 3. Can you see that?
Yes, sir. Yes, sir.
Good. Don't put this up here instead. Make this a little smaller. All right? Because I'm looking for the 5 to the k in this. So therefore, what it means, because I break up this 5 to the k plus 1 and put it as 5 times 5 to the k. Because this is 5 to the 1 times 5 to the k. Now. So that's why I get that. So this now is the 5 to the k that I have there. So I can take this thing here now. It's a different color. I can take this thing that the 5 to the k is equal to and drop it in there. So substitute it in there so for the 5 to the k. Because I want to see what this expression is equal to. This expression must finally be equal to 2 times something when we're done. But I have to induce this result in here because it's proved by induction. So I'm going to work this out now. So this then becomes equal to 5 times, and the 5 to the k becomes 2q minus 3. 2q minus 3. And I'm adding back this 3. All right? Remember, all of this must equal 2 times something, you know. So I'm going to expand this out now, and I'm going to get 10q. And it's going to be 5 times 3 is negative 15. And negative 15 plus 3 becomes negative 12. And this can be factorized with a 2. So it becomes 2 times 5q minus 6. Remember, I know, because this q is an integer, it means that this whole expression is an integer, because I have a 5 times an integer minus another integer. So this whole expression is an integer, and therefore we have shown it. This expression is equal to 2 times an integer. So therefore we have shown that this is a multiple of 2. So it means that right here it is shown that pk plus 1 is true. But it is true if pk is true. Why am I saying this? Because remember, we use the result from pk to prove the result for pk plus 1. And so pk plus 1 is true if pk is true. And once you can do that, once you end up with this stage, once you show that stage, then you can draw your fourth line, your fourth statement. Your fourth part is to write a conclusive statement. And this part, to write a conclusive statement, carries marks. If you don't write this conclusive statement, because it's a process, it's a proof, you're not going to get the full marks. And a conclusive statement is what we have there, is that, therefore, by mathematical induction, you have to spell it out. I'm just abbreviating it now. Therefore, by mathematical induction, Pn, the original statement that we started with up here, that we call Pn. Pn, the original statement, is true. Is true for all n which are natural numbers. That is how you prove the divisibility type. That is it. But understand that?
Yes, sir. Yes, sir.
Yes, sir.
All right. All right. So I said Tori Isaac, and I said David, and I said Jelisa. So you guys can tell me what questions you want me to do. I'm going to do a couple of these induction questions for the guys here. And then I think you want to do some, what is it, some integration, some vectors. You can let me know what topics you want me to do. I'm prepared to work a couple of hours here with you.
Could you do?
Say that again? Just see my breaking up, yes?
Could you do question 4B? Could you do question 4B?
On this paper?
Yeah, on this paper. Yes, sir.
You must try the one topic at a time here. Try the one topic at a time. But anyway, question 4B. This one right here? All right, let's go. Because what you want to do is do a number of the same kind of question until you kind of stick the process. When you're all over the place, you don't get a chance to make the information stick. But let us do it still, all right? But let us just try the one topic at a time. We do a number of questions on one topic, and I get the good feel of it, and then before you move on to another topic. That way, the method will stick. Because if I do another induction question, what will happen is that you will see the same kind of process happening. And you see it a couple times consecutively, and then it starts to stick. So I would say, save this question for another time. You can make a note of it. I will come back to it. Let us exhaust the induction questions for the time. All right, since we have started with that. All right. So tell me which other paper has the induction on it. Have anybody?
2014.
Anybody in the 2014?
Yes, sir. 2014.
All right. Let me check that. Let me check that. 2014. 2014. Okay. What number? You know what number? Oh, this is still one that I have to write on the side. Okay, so I have to split the screen again. It's not yet one of the papers that I can write on. Okay. All right, so this is it, right? All right, good. So this is a proof by induction. But this now is the summation type, right? That's the summation type. The approach is different for the summation type. What I normally do with a question like this is establish an expression for what the sum is over here. All right, that's what I normally do. And it is shown in this expression. You're really summing that expression here. So instead of writing my summation like this, I prefer to say that this side of it. So we're doing this question. Right, we're doing this question, number that one. I prefer to say that this side of it, really writing it as a summation, it represents the sum from r equals 1. I can just say from 1 to n. Say that last term is n of the expression. And this is a general expression, but instead of an n, we're going to put an r because this represents the last term of this sum. That's why the n is there. So we need a general expression now. The general expression is done with the same thing here, but we replace this n with an r. So really summing 2r minus 1 squared. That's what we're really summing. All right? When r equals 1, we get this first term. Then when r equals 2, we get this second term. When r equals 3, and r equals 3 here, we get this third term. And this last term is when the r equals n. And what we're saying is that this sum is equal to this expression. So that is the summation type. All right, so let's attack this up. So this is equal to n over 2 into 4n squared minus 1. And this is for n is an integer. So really and truly we're proving this. I'm in the exam and they gave me this. I'm going to write my statement as this because it is the same thing. All right, because you want to stick to one consistent way of doing the questions. So you want the questions to appear one way to you. So that is what I'm proving because this is the same as this. All right, so let's continue. In addition to that, this is more compact.
Sorry, I have n over 2 instead of n over 3.
It's over,
you have n over 2 instead of n.
Yeah, all right, cool. Right. In addition to that, this is a more compact way of writing out this expression. All right, rather than to write out all of those terms. So let's go. Start the same way. You're gonna say let statement Pn be such that you're gonna write this thing. That's what you're writing. So the sum, we can just copy it across then, since it's the same thing I'm writing. So that write it all over again. Space it over here. I prefer the paper nowadays, okay? Just write on the actual paper itself. All right, so let Pn be such that, as is the case for n is an integer. And this is a summation type now, guys. The method is different from the divisibility type. All right, I'm recording this session. You can go back and look at the video. if anything. So you can practice, right? So the steps are the same 4 steps. Generally speaking, the same 4 steps, but the induction phase approach is different for the summation type. All right. So step 1 is to prove that this statement is true for n equals 1, just as we did before. So for n equals 1, you basically plug in 1 inside here. So for n equals 1, the r is 1 to n. The r is 1, and you're going to put 1 up there. And what is that? What should that mean? That the left side and the right side should be the same value. So for n equals 1, r is equal to 1. So this statement becomes the first term, which is what we have here, is really 1 squared. We have it over here, is 1 squared work out. We're going to write it still. It becomes 2 times 1 minus 1 squared becomes equal to, the n is 1. So it becomes 1 over 3 into, this also is 1, into 4 times 1 squared minus 1. Or we can say the left side equals the right side. That's another way we can do it. We can work on what the left side is, or the right side is. Let me do it that way, because I do it that way sometimes. So we can say, okay, the left side, which is this side, the left-hand side, is equal to this. And we'll see what that is. That works out to be 1 squared, which is 1. And then the right side now, which is this side, work out what that is. So when I say the right-hand side of the expression is also equal to 1. Because if you work it out, you're going to get 1. Because inside here is 4 minus 1 is 3. Then inside here, work out to be 3. Then the 1/3 of 3 is 1. So the right side is also 1. So the left side and the right side is the same for n equals 1. And therefore, the statement is true for n equals 1. For n equals 1, the statement is true. So P1 is true. So you can write that here. P1 is true. That is required in the induction proof. You have to prove that it is true for the first value of n. All right. Sometimes the n will start at 2. You know, there are occasions where the n is for greater than or equal to 2. Right? Sometimes you have that case. In that case, it will start at 2. Then you're gonna go now for n equals 2. For n equals k, the second step. Second step is just a writing down step. We say now for n equals some value k anywhere in the sum, and you're gonna basically substitute the k now up here. Wherever you have n, you're gonna put the k there in that original statement. So like you're finding pk, right? So the statement becomes that the sum. So it's almost like I write about this thing. I'm changing the n to k. So I'm just copy it. Instead of write it, I'm just copy it. So you can see that is exactly what is happening. So I'm writing about this whole thing, but just that I'm replacing the n's with k's. That is all. So I'm writing about the whole thing. Just that now this n right here becomes a k. And this n and this n each become k. So I'm going to delete this one and delete this one. Replace them with k's. So put a k here and put a k squared there. All right. So basically, we assume it is true for n equals k. All right. So here we assume, to begin with, that pk is true. All right. That's the easy step. Replacing the n with k. Then we'll come to step 3 now, which is the induction phase. This is where you do the work. This is where you do the work. So for n equals k plus 1, and this is where it gets dicey now. So for n equals k plus 1, you're going to set up the summation for n equals k plus 1. And the logical thinking, you know, to get the sum from 1 to k plus 1, it is equal to the sum from 1 to k plus the k plus 1th term. So let me write it out. This sum, okay, put in the k plus 1 and the sum here now. You know. So the sum from 1 to k plus 1 of the same expression, 2r minus 1 squared, becomes equal to the sum to k. So put in the sum to k here now. Now that is how the second step is induced into the third step in the summation type. So you're taking the sum to k, which is this expression I'm going to put here, equal the sum to k. So I can literally copy this and paste it here. Equals the sum to k. Let me shift this down because I don't want that space to write. Let me shift this down and put it under here. So it becomes the sum to k. The sum to k plus 1 is equal to the sum to k terms plus what we call the k plus 1th term. K plus 1th. K plus 1th term. So the sum to k plus the k plus 1th term. Now, what is the k plus 1th term? The k plus 1th term is simply when the r is equal to k plus 1 in this expression. That is all. So just that expression with the k, with the r equals k plus 1. Let me write this better. K plus 1th term. So the k plus 1th term is when the r equals k plus 1. So take the k plus 1 and replace the r in this. And then now what we normally do is write down what we are supposed to get for the pk plus 1 and work towards it. All right? Write down what we're supposed to get. I'm going to write down what we're supposed to get right here this time. So what are we supposed to get? Let's write it down. To get. We normally write it down, scribble it down somewhere so we know what we're working towards. So when the n equals k plus 1, our expression over here is supposed to eventually come to a case where you have a k plus 1 for the n up there, so, and a k plus 1 for the n inside there, so. Right? So let me look at it. So where this n is, I'm supposed to get a k plus 1, and where this n is, I'm supposed to get a k plus 1 when that third phase is completed. That's what is supposed to happen. So let's write out what we are supposed to get. So same expression I'm looking at over here. So this n is supposed to become k plus 1, and this n is supposed to become k plus 1. So I'm supposed to get k plus 1 over 3 bracket 4 times k plus 1 squared minus 1. This is what I'm supposed to get. So this whole expression right here is supposed to work out to that. So I know what I'm working towards. All right? So let's go now. So remember though, that this expression, the sum to k, is actually equal to this. It's the first thing, right? So I'm going to put this here for the sum to k. All right? So this thing now is going to be equal to this first. K over 3 into 4k squared minus 1. And then, as I said, the k plus 1th term is that basically taking the k plus 1 and putting for the r in this. So I'll put the r in there for the k plus 1th term. I'm going to get plus 2 times k plus 1. Now we're at a space. 2 times k plus 1. Let me shift this over. 2 times k plus 1. Let's write this again. Hope you're following with all this erasing. 2 times k plus 1. I'm substituting this inside here for the r. And then I have to subtract a 1. And then I have to square it. See? Square it. So it's everything that I have right here so now is supposed to work out to this thing. And that's what your task to do. That's why phase 3 is the working phase. Step 3 is the working phase. So your algebra have to be good now. You have to be able to rearrange and transpose and factorize and so on. Inside here, I see this as the square completed. I've completed the square inside here. But you need to factorize. The first aim is to try to get this k plus 1 over 3. That should be your first aim, to get that k plus 1 over 3. All right? But let us continue. I'm going to have to factorize with a k plus 1 somewhere in here. But let us continue. So we're working on this thing now. And our aim is to arrive at this. All right? So let's go. All right, so I'm going to expand out everything first. All right, so I'm going to expand out everything. All right, I'm going to work on getting my 1/3 first. So to get my 1/3, you see this expression, I'm going to multiply by 3/3. So I'm going to shift it a little bit to the right. You have to develop these skills, guys. So to get my 1/3 that I need, to get the 1/3 that I need as a factor, I'm going to multiply this term by 3/3. This already have a third on it. I'm going to multiply this by 3/3. So I can factorize a 1/3 right away. So I'm going to get this equal to 1/3 into. So I take out the third out of this, I'm left with k times this. I'm going to express as a cubic, so it becomes 4 times k cubed minus k. But that's standard so far. And I factorize the third out of this, and I'm multiplying this k. K times this give me 4k cubed, and the k times this give me this minus k. Then over here now, this third is factored out. This 3 remains. I'm going to get a plus 3 into, and I'm going to write what this is really. I'm going to expand the square. But what is this inside here, so really? What is it really? Let's look at what it is and write it out in red. Inside here, really what we have is 2 times k is 2k. Then we have 2 times 1 is 2. And 2 minus 1 is 1. So we really have 2k plus 1. This really works out to 2k plus 1, and I'm squaring it. So all I'm going to do now is expand the squared term of the 2k plus 1. Your algebra must be good. So when I square this expression now, I square this first, I'm going to get 4k squared. Then twice the product of the 2 is my second term in a perfect square. So I have to multiply these two things. I'm going to get 2k, and double that, I'm going to get 4k inside here. And then my second term squared is a 1, so I'm getting a plus 1. That's what I have in the bracket. Let's go further and expand this out and put it as a cubic function that we're going to have to factorize a k plus 1 out of it. All right? So this then becomes a third still out here into. So this is my only cube term. So I'm going to write it as 4k cubed. And then now looking for my k squared term. So this is going to give me a k squared. This 3 times 4k squared is going to give me a k squared term. That is 12. 12 k squared. Then my k terms now. So I have a minus k here. And this give me 12k. 12 minus 1 is 11. So I'm getting 11 k's. When I look at my k's, I'm getting 11 k's. So I'm plus 11k. Now look at my constant values now, which is just this 3 times this 1. That's my only constant value, which is a plus 3. And that is it. So far, so good, guys?
Yes, sir. Yes, sir.
All right.
So where did the lever key come from?
Where what?
The lever key.
Now look again. 3 times 4k is 12k, right? Minus the k right here. So you see it?
Oh, yes, sir. Yes, sir. Okay. You
have to look for all the keys and consolidate them. So out of this now, I'm trying to get a factor of k plus 1. See, I need a k plus 1 up here. So I know that k plus 1 factor is in this now. We can do a division and divide it by k plus 1 to see what it comes out to. But you can do, there's a method of reducing it. And some people use the what do you call it, the synthetic method to factor it out, to factor the k plus 1 out of it. But there's a way of reducing these values down and make them all be factors of k plus 1. So you can factor the k plus 1. Watch this now. Watch this now. This becomes easy. So if you remember, you know, if you want, you can divide it by the k plus 1, you know, and put this under here and divide it out, you know. You can do that, you know. Just divide it by k plus 1 to get the k plus 1 factor out here, you know. But let me show you like a method that you could maybe use, especially when it's a value like k plus 1, which is pretty common. Watch this now. This becomes equal to a third into. Watch this now. See, because this is 4k cubed, I need a 4k squared out of that. Because this is 4k cubed, I need a 4k squared out of that to put with the 4k cubed. Watch it now. So I'm gonna get 4k cubed plus 4k squared. So this now has 4k squared plus 8k squared. See that? I'm gonna have this 4k squared right here. So it's because I have this 8k squared left to put back here. Let's put it. So I'm gonna have 8k squared. All right. Then now I need a 8k out of this to put with the 8k squared. So I break up this 11k with an 8k first. So I'm gonna put plus 8k out of this, and I'm breaking down this into 8k that I have here. What I have left? I have a plus 3k left that must go there. So I break up that 11k into 8k plus 3k. So I have plus 3k. So I'm putting these two together. What I'm doing now, I'm putting these two together, and this is a 3k now. Let's put it with the plus 3. So I'm gonna put plus 3. All right. So what you find then is that I can factorize k plus 1 out of this. Look at it. I can factorize k plus 1 out of this, and I can factorize k plus 1 out of that. So then I can factorize the k plus 1. So look here now. This becomes equal to k plus 1 over 3. Now look at this. If I factor k plus 1 out of this, I'll put it this way. This that I have underlined is the same as 4k squared into k plus 1. You can see that? This expression right here is same as 4k squared into k plus 1. That's what this is. And I'm putting the k plus 1 outside. So this whole thing is just going to be left with a 4k squared. But the k plus 1 gone outside here already. Right? So this becomes a 4k squared. Then this 2 now factors with an 8k. So this 2 becomes 8k into k plus 1. When I factorize this 8k plus k plus 1 out there, I'm going to be left with this 8k. So these two, when I factor out the k plus 1, I'm going to be left with a 8k. And then these two now factorizes into 3 into k plus 1. So now factor out the k plus 1 out here, I'm left with this plus 3. So I'm going to put the plus 3. And so I am on my way to this. Remember, this is what I'm trying to get to now. And I wonder if you see it now. Because all I need to do inside here, so now, guys, is complete the square. Complete the square inside here, I'm a good. So all I need to do now, complete the square of these two terms, and I will get that. Because that's a perfect square, so I have to complete the square. So I need to complete the square inside here now. So watch it now. So this becomes equal to k plus 1. I'm telling you from now, this is 2014. They don't set them like this anymore. They tend to give some like a baby easy one these days, right? So I wouldn't worry about it. Into, I'm going to complete the square of this. Now, to complete the square inside here, remember you factorize the 4 out of this first. You're going to get 4 into k squared plus 2k. Come, push the door and come. Yeah, man, thanks. Let's just sit down on the table. Thanks. And then plus this 3, yeah, thanks. Plus this 3. So your algebra for good now, guys. Go on over to the next page. Then I'll complete the square inside here. So now complete the square. So I get k plus 1 over 3 into 4. Complete the square inside here. So now I get k, half of this 2 coefficient is a plus 1. put on the square, and then subtract the square of this. Remember, you have to subtract the square of this, which is subtracting a 1. And then put back this plus 3. And see there, I have it now. Right? And factorize that 2 as well. No, where is it? Where is it? Purpose it there. That's what I have. Let's see. That's what I have. No, something wrong. Something is wrong. Because I'm getting a plus 2 instead of a minus 1. I'm getting a plus 2. Let's check this up here. Something is wrong. That's what we're supposed to get. Because the n becomes k plus 1 square minus 1, 4 there. I know what that. When I factorize out this 4, right? And I'm computing square inside here, I have to put back this. On this. Right. Plus 3. With a different bracket. Right. So after I factorize the 4, right, inside here, put a different color around this bracket. And I'm computing the square inside here, right? This is all inside this red bracket. Right? Because it's the k plus 2 squared that factor that computes square into that. That's what happens. Right? And so now I'm going to expand with the 4. All right, it's going to work itself out. So this becomes k plus 1 over 3 into, I'm going to expand with the 4 now. So it becomes 4 times this first, which gives me 4 into k plus 1 squared. And then 4 times this 4 is negative 4. Negative 4 plus 3 is negative 1. See that? That's what we wanted to get. That's what we have got. Take a lot of steps for this one, but that's how it is sometimes. But that is it, you have gotten it. And since you have got this now, see? This is the n when the k plus 1 and this is the n equals k plus 1 and then we can see here that pk plus 1 is true if pk is true. That's the third step. Because you have completed the third step, you can write a fourth step, which is a conclusion step. You're going to say, therefore, in blue. Therefore, fourth step is therefore, by the process of mathematical induction, the original statement that we call Pn is true for all n which are natural numbers. For all n which are natural numbers. And that's a proof. How are we with that? Okay with that?
Yes, sir. Yes, sir.
All right. All right. All right, Tessima. Want another one of this topic and we'll do something else?
Maybe we can do another one.
Yeah, tell me where we have another one. David, which question you want to do, David?
Yeah, 2017.
2017? Huh?
Number 1D.
1D? That's an induction question as well?
Yeah.
That's an induction question as well. All right, 2017 1D. Let's see. Let's see other classmates gone, man. What, they want to do something else?
Probably want to study biology.
Oh, biology. When is biology?
Thursday, I think.
Okay. All right, I understand. See if we can do some work every day. This is it? This is a question? This one, right? Yes, that's another summation type. That's another. This one is far more easy. Far more easy than the one that we just did. And this one we can write on the paper, so we can use the whole screen now. So first thing, as I said again, I'm going to compress this side and write it as the sum from 1 to n of 8r. But that's what it is really. 1 to n of 8r is equal to this expression, 4n into n plus 1, where n is an integer. And I'm going to say, let this be the statement now. Let Pn be such that this is a statement. All right, to begin with. Then it's the same process. Let me see how much space to give to work. All right, I give a whole page. So it's the same process. Step 1, which is for n equals 1. For n equals 1. All right, you're going to show the left side and the right side is the same. The left-hand side, because it's a summation type we're doing, is 8 times 1, which is 8. And the right side over here is 4 times 1 into 1 plus 2. 1 plus 1, sorry. Because this n is 1 and this n is 1. So this also works out to 8 because it becomes 4 times this 2. This is also 8. So they're giving us the same value. So then we can say P1 is true. The statement is true for n equals 1. Then we go to the second step, which is the easy step. You just basically put in n equals k. So for n equals some natural number k, because n is a natural number, so whatever value you give to k, to n, it's a natural number. You're just replacing the n now with k in this expression up here, and down here, and over there. All right, so the statement is then going to become that the sum from 1 to k, we're doing this line now, putting k on it, of 8r becomes equal to 4k into k plus 1, right? And here we're assume that pk is true. Some teachers will say, assume the statement is true for n equals k, but I already defined the statement as pn. So if I put pk, it means that I'm saying the statement for n equals k. Same thing. All right, then we'll come to the induction phase, which is a working phase. Step 3 is where you do the work in these questions. For n equals k plus 1, remember now it's a summation type. So you do the sum to k plus a k plus 1 term. So the sum from 1 to k plus 1 of the same 8r will be equal to the sum to k from 1 to k of the same 8r plus 1 more term, which is the k plus 1 term. What is the k plus 1 term? Simply term when the r is equal to k plus 1. So we're going to take the r equal to k plus 1 and put it in here to get that term. And then this term is this. We're going to write what we're supposed to get. What is this supposed to work out to? All right, I'm going to put it right here in purple to get. What are we supposed to get? To get. Right, what we're supposed to get. So what we're supposed to get is that the n here and the n here must become k plus 1. So we're supposed to get 4 times k plus 1 bracket k plus 1 k plus 1. That's this n is k plus 1 plus another 1. So we're supposed to get 4k plus 1 k plus 2. Right? So when we get this, we're good. It's easy. It's going to be a quadratic that will factorize into that. So this statement in blue This thing in blue is supposed to work out to this in the end. Let's continue now. So this statement here now, bam, continuous, is a sum from 1 to k plus 1 of the 8r is now equal to now. This first thing is this. Right? Because remember, the sum from here is the same sum to k now. That is equal to this. So it is 4k into k plus 1 plus the k plus 1 term now, as I said, is when you put the k plus 1 for the r right there. So you're going to get 8 into k plus 1. And it becomes very easy because, firstly, we can factorize the k plus 1. In fact, we can factorize 4k plus 1. But this is what we're working towards. You know. We already can factorize this 4k plus 1. We have it in this 4k plus 1. We can factorize 4k plus 1 out of this. So already we can factorize the 4k plus 1 in bracket. All right. We'll factorize it out of this one. It becomes just k. The 4 and the k are factored out here. So I'm left with this k inside the bracket here. K. And if I factorize 4 out of this 8, I'm left with 2. And the k plus 1 is factored out here as well. So this is now just 2, which is what I want. See there? That's it. See that? I say I write to get this. I said that I'm supposed to get it and I've gotten it. So this then means that pk plus 1 is true. So this statement now therefore means that pk plus 1 is true if pk is true. And then you have to write a conclusion. You have to write a conclusive statement down here, number 4. Step 4 carries a mark even if it's just a statement you're writing. It's a part of the process. And I said, therefore, by the process of mathematical induction, you write it out. The original statement Pn, the original statement up here that we call Pn, this original statement is true. Pn is true for all n which are natural numbers. And that is it. All right, that is it. We can maybe see if we can do one more divisibility type. There's also an inequality type that they don't set very often. Right? I've not seen it in a while. But there's also, you have any other divisibility type? We have done 2 summation. Any other divisibility exists that we can just look at quickly and then we can do another topic.
I believe 2021 in 1D that divided.
All right, 2021. 2021. 2021. This is 1D. Yeah, that's it. No, that's not it. 2021. That's not it. It's a different question.
Sorry, I think you passed it already. Scroll up, back.
And this?
Scroll up. Sorry, you passed it. Scroll on back. Scroll up. Scroll on a little further.
That's
supposed to be that.
following rules. No, man. That's
Oh,
not
no, it's
that.
not. That is not. That is not
It's a
that.
factor in the theorem. See if we can find it. It's not this paper. It's a different question. I don't think it would come. Let's see if it possibly come anywhere else. Possibly. Nah.
So you could check the 2019 paper. 2019 or 2017, one of them.
I just did 2017.
2019.
Let's see. So what you guys need to do now is just look through the topics, look for the questions, on the various past papers before you come that you want me to do, so that, you know, you just tell me where they are. So we don't waste time, we have a more efficient process. All right, so 1 year. So this thing now is divisible by 4, right? And it's to prove that one. And how much space to give? To give a page and a half to do it. All right, so this is the divisibility type again. We can maybe see if we can find an inequality type plus 1, and I'll do that one for you because the approaches are kind of different, right? All right, so they said that this expression is divisible by 4. So it means that this expression is equal to 4 times some quotient, right? So we can write the statement that says let Pn is such that the expression 5 to the n minus 1 is equal to 4 times some quotient x, where that x is a member of integers and the n is a member of a set of natural numbers. That's our statement. Same process again. Step 1 is to prove that it is true for n equals 1. For n equals 1. Although it's the left-hand side, right-hand side for this type, right? We just plug in the 1 in there and show it equal to 4 times something. N equals 1. Just plug the 1 inside here, and the answer will be 4 times something. So it becomes 5 to the 1 minus 1 is equal to 4, which is 4 times 1. This works out to 4. And this therefore means that P1 is true. This means that P1 is true. Simple as that. Then second step in the process is to show that it is true for n equals k, or assume it is true for n equals k. So I take this and drop it up here, up on this one. And I want to change this quotient to q. Let's do the same every time. So for n equals k, this statement could become 5 to the k minus 1 is equal to 4 times some different quotient. I want to tell him that that quotient is a member of the set of integers, same way. And your n is a natural number. The k is a natural number because they give him k that value. So you have already defined your n as natural numbers. So just like the one that we did before, you make this a subject and try to substitute what it is in the next phase. I'm going to make it the subject from now. When you practice these things, you know. So when I write 5 to the k equals 4q, this one going to come over and become a positive 1. So we're going to look to use this expression for 5 to the k in the next step, right? In the induction step. So in step 3, which is induction phase of the proof, we're going to go for n equals k plus 1. Remember, you know, don't write what it is equal to yet. It will work out itself. This is a step where it's going to work out itself. So we're going to initially put this up here again. We're not going to write with equal to. Let it work out what it's equal to for itself. So we're going to have 5 to the k plus 1 minus 1 equals. What are we putting after the equal? We're putting what this expression continues to be equal to after we break it up, so that we can substitute this down into that line. That is the process. Don't go put in a 4 times. Let it work out itself. At this step, you have the 4 times whatever work out itself. Just break this up with the aim of using this in it. That is your aim at this step. All right? Because you have to induce the second phase into the third phase of the proof. All right, so I'm going to split this up again. I think it's the same kind of thing. It becomes 5 times 5 to the k, and then it's minus 1. And then because the 5 to the k is equal to this in step 2, we can take this expression and drop it inside here for the 5 to the k. And so it becomes now equal to 5 times 4q plus 1 minus 1 out here. This is this minus 1 out here. We're going to expand this. We're going to get 20q. Then 5 times 1 is 5. And that 5 minus 1 is 4. So it becomes 20q plus 4. We can factorize 4 out of this. Let's do it down here. So it then becomes 4 into 5q plus 1. That's what it becomes. Remember, q is an integer. So 5q is an integer plus 1 remains an integer. So this expression is an integer. So therefore, it is true for n equals k plus 1. So we can write that statement now, that pk plus 1 is true. It's true. I must say if pk is true. Why am I saying if pk is true? Because remember, we use the pk result in the pk plus 1 result. And we got this expression. So it is true if the pk is true. And once you reach there, you can draw your conclusion again. Step 4. Draw your conclusion, which is to say, therefore, by the process of mathematical induction, the original statement Pn is true for all n which are natural numbers. All right, so I've done 2 summation, I've done 2 divisibility. Let me go and find an inequality. Huh?
You could scroll up for a second.
See there? Let me go and find an inequality type for you. I don't set it very often. I think they set the inequality type maybe 2 times in the past. I don't recall seeing any since I started this new syllabus that you guys do. But let us just do one still and show you what the thought process is for that one. Because for the inequality type, kind of tricky because we tend to work in equals. We tend to always be balancing equations and adding to both sides or subtracting from both sides the same value. Because of the inequality type, you just want to do actions that are true and you're working towards what you want to get, you're supposed to get. All right, while stating the truth along the way. So let me look at the worksheet from the class for that. How we did that topic. All right, so let me look at it from here. It's mathematical proof, right? Proof by induction. Where is it? That's of proof. And this is the worksheet right here. It's supposed to be in this somewhere. All right. So the inequality type. I had it in my examples somewhere. Where did the topic? Right, see here. This is it right here on the screen that you're looking at right now. That's an inequality type. Okay? You're proving this thing. Proving this. For n greater than or equal to 3. All right. So let me go through it. Show you. Here. That is one. I think there are others on this sheet down here. There's another one down here. So n squared is greater than n than 2n for n greater than or equal to 3. That's another one. You're not gonna see a lot of them. All right. All right. Let me see. I wrote this one. All right. So I'm explaining this solution here now. Walk you through it. So this was to prove that this was to prove that 2 to the n is greater than n plus 4 for n greater than or equal to 3. N is an integer. So you're starting at 3. Right? So you're starting at 3. So you write the statement the same way. You can basically let Pn be this. So we're going to say let Pn be such that, and you write that. So to give you this to prove, you make the statement with that. We're starting at 3. It's starting at 3. So step 1, starting at n equals 3. So for n equals 3, left side becomes 2 cubed, and 2 cubed is actually 8. And the 8 that it is equal to is actually greater than 3 plus 4. 3 plus 4 plus 8 is greater than 7. So that is true. So you can say it is true. So P1 is true. Something like that, right? But the left side and it is 8, the right side is 7, left side is greater than the right side. So that is true. Then the second step, it's a simple step, which is for n equals k, and k is greater than 3, you know, n equals k, it has to also be greater than or equal to 3, right? But it has to be greater than or equal to 3. N equals k, k also has to be greater than or equal to 3, but it's the n value. You're gonna have the right, but this statement with the k in it. So you're gonna have root to the k is then greater than n plus, not n, k plus 4. K plus 4. All right. So here now you assume that PK is true. All right, see what step now? Step 3. And remember this. This is now for n equals k plus 1. So for n equals k plus 1. So you're taking this k plus 1, you're dropping it up here first. But the important thing is that you don't put back on inequality part yet. Right, but the 2 to the k plus 1 is equal to first, and you're looking to see how you can incorporate that in it. All right, so I'm going to write it first. So I'm going to write 2 to the k plus 1, put that it equal to first. Don't put a greater than sign. Put what this is equal to first, and you're trying to see if we can use this in it. All right, now what is this equal to? To be good if I can pop out the 2 to the k out of this. All right, so see here now it is equal to 2 times 2 to the k. What is now? Remember now that this statement is that 2k is greater than this. And now we have 2 times 2 to the k. So if I multiply this inequality by 2 to get that, right? If I multiply that inequality by 2 to get that. Okay, now this inequality that I have in phase 2. If I multiply by 2 to get this expression, 2 times 2 to the k, then the left side, let me shift this down a little bit. The left side will become 2 times 2 to the k, greater than or equal, not greater than or equal, greater than, multiply this by 2 as well, I will get 2k plus 8. So what do I know? This expression that I have on this line is greater than 2 to the k plus 8. 2k plus 8, sorry. this thing right here, because it is here, it is greater than 2k plus 8. So this thing that I now have, I can put it that it is greater than 2k plus 8. Now, here again, we have to know what we're working towards. And we're going to write down what we're working towards. And we have to get it somewhere down here. And we have to tell the truth each step of the way in working towards that. What are we working towards? When we plug the k plus 1 on this side here, you basically want it on that side as well. So you really want to show what are we supposed to get? Let me put it in a box right here. What are we supposed to get? To get down here, so put it down here, so down here, so down on this line. We want to get that the 2 to the k plus 1, which is what this side is greater than, and then here we're going to put k plus 1. So it's supposed to be k plus 1 plus 4. K plus 1, that's what this is, k plus 1 plus 4, which is k plus 1 plus 5. So that's what we're trying to get. All right? Remember now, guys, that the k is greater than or equal to 3. That don't forget it now. Don't forget that, you know. K is greater than or equal to 3. All right? So watch this now. You see the expression here? I'm keeping an eye on this. I'm trying to get this over here. All right? Watch this now. I'm not going to tell any lies. See this expression? See the k, 2k part of it is greater than k. And see the 8 is greater than 5. Okay, remember, you know, this 1 plus 4 is 5, you know. So I won't be telling it any lies if I say that this expression that I now have is also greater than k plus 5. Because the 2k is greater than k, and the 8 is greater than 5. But understand that? But understand
Yes,
that?
sir. Yes, sir. Yes, sir.
Good. And so this, I can draw the conclusion and say, therefore, this thing, which is equal to this, where this is now greater than this, so let me say this greater than this now. And then now, this now is greater than this, so it still means then that also this is greater than this. So I can put this now greater than my result that I want. So I can say, therefore, 2 to the k plus 1, in fact, is greater than k plus 1. So I break up the 5 here now, plus 4. Stop showing it. That's how the inequality type is done. You have to do one like a juggling, right? Another step right there, so, and say something that is the truth, but you have to keep an eye on what you're working towards. So this means that pk plus 1 is true right here. Pk plus 1 is true if pk is true. All right? And I'm going to draw the conclusion now. And so therefore, step 4, which is to say, therefore, by mathematical induction, the original statement Pn is true for all n which are natural numbers and where n is greater than or equal to 3. That is it. Think on all right there, sir? Think on all right with that?
Yes, sir.
The thing about it, I don't they setting in the equal. They don't even set on every paper. Maybe one day we can come back. Write down that one and challenge yourself with it. This one. Write down this one and challenge yourself with it. And tell me what you get. You have to do it now. All right?
Oh, do that one now?
No. I said write it down
Oh,
and do it yourself afterwards. I can deal with it again after this class.
All right.
So David, since you're here, which topic would you like to do? Which question?
Well, I'm not sure exactly what numbers there will be in the past papers, but
What
integration by substitution.
Integration in a substitution method. All right. All right, let's look at some of the recent exam papers. You might have some on it. Integration by substitution. It's quite straightforward. It's not complicated. If you do a couple of them, you'll see it. All right. It's usually one of the back of the. Let's look at 2022 right here. See if there's any on it. All right. So when you guys coming back, I'm gonna have a session tomorrow. I'm gonna have a session Wednesday. You pure maths is Friday or Thursday?
Thursday.
It is pure maths. Thursday? All right.
Yes, sir.
Not have to go on a day. Not have to go on a day Wednesday or something. Not have a school work. Go on a day. What time can be available tomorrow? Or what time? Can we start early and run a session with them tomorrow? What time you guys can be available tomorrow? You have exam tomorrow?
No, sir.
You have exam Wednesday?
No, sir.
Oh, you're free. Remember why you binge the multiple choice I'm still in. Did I send some multiple choice in the group with answers? So you guys can look through. It's a substitution method question here. It's a substitution method question. I'm going to deal with this one. All right. So the question is telling us to use the substitution here to solve that. I'm going to tell you what the key thing is now. The key thing, even if they did not give me this substitution to use, looking at this, to integrate this, I would know that I have to substitute u equals this inside here. Why is that? Because when I differentiate what's inside here, I am basically getting what is outside here. When I differentiate inside here, I'm getting a 2x. I'm getting a linear function 2x, which exists out here. And once that is the case, when I differentiate expression inside here, it basically exists out. Because I see this 4x here, it can be cut up into, factor it out and get back 2x and put 2 out there side now. So whenever the expression within, because this is on a power, whenever the expression within, the differential of it, which is 2x, exists as a multiplier, then a substitution to make is u equals the expression within. U equals the x squared plus 1 is the substitution to make. All right? But they are helping you by telling you to make it. They tell you the same substitution I would have made, they are telling you to make. But let's look at it now. So making a substitution, u equals x squared plus 1. Now, we need to be able to substitute for the expression in here, out here, but also have to be able to substitute for the dx. So I have to differentiate this expression. When I differentiate the left side, which is u, I'm going to get 1 du. So I'm going to get 1 du. I don't need to show the 1. When I differentiate the right side, I'm going to get 2x dx. Now, some teacher would have said differentiate du by dx first and get 2x. And then I take this dx and multiply it across here. But why do that? You don't have to do that. Once you differentiate a function of u, not with respect to anything, you get 1 du. You just put 1 du. Here I'm differentiating a function of x, not with respect to anything. Differentiate it, the normal way we get 2x because I'm not differentiating with respect to anything. But I differentiated x and multiplied by dx. So du is equal to 2x dx. I'm looking for the 2x dx inside here now. So I can replace it with the du. That's what it is. How do I find it? You see, this 4x, as I said, I'm going to split it up. So first I'm going to call this integral I. All right? I'm going to break up this side. So the I is going to become, I'm going to factorize the 2 out of this. Put back the integral. This 2x that is left, I want it beside the dx because I'm trying to generate the 2x dx. So I'm going to put back x squared plus 1 to the 5th power. And then the 2x that is left out of this, so after I factorize the 2, I'm going to put it beside the dx. So I'm going to have 2x dx here. Understand that? Because I was trying to get this thing that I have here. Now I can make my substitutions. My integral then becomes 2 times the integral. This expression in here is u, so I now have u to the 5th power. This 2x dx is du, so I now have du. So it becomes something simple. E equals 2 times u to the 6th power over 6. Don't forget your plus k, because there are no limits, or plus c. K or c, don't matter. And then now what you do at the end, for the u is this. You're going to take this x squared plus 1 and substitute back for the u in the answer. And recognize that this 2 over 6 is just a third. So this integral then will become a third. And the u is x squared plus 1. I'm raising it to the 6th power and adding on back my c. Understand that? Understand that, David?
Yes, sir.
Yes.
All right.
Yes,
now,
sir.
now let me show you something now if the question had limits on it, right? Let's do it over. So let's do it back up to here if it had limits on it. So let's say they had given us some limits on the integral. So let's say this was from, let's give it some value. Let's say it was from 1 to 3. This 1 and this 3 are x values. When I change the integral to u, I need those limits to come to the corresponding u values. So initially, the limits would come back on this line, 1 and 3. Right? But I need to see what the corresponding values is over here as well. So as I see what the differential was, I need to see what the values are, the limit values are. So this one is when x equals 1. So I'm going to write it. When x equals 1, plug the 1 here, the u is equal to 2. And when x equals 3 up here, plug the 3 here, the u is equal to 10. If I get 3 squared plus 1 is 10. So I have the same limits here right now, 1 and 3, because I'm still integrating with respect to x. When I substitute into the integral and change the limit, all right, I change what I'm integrating with respect to. I'm now integrating with respect to u. So I need a corresponding u value for this down here, which is a 2. And I need a corresponding u value for this down here at the upper limit, which is a 10. And then I proceed normally with that. So this integral would have become now 2 into u to the 6th power over 6 same way, but this time you're doing between limits of 10 and 2. This over this is still a third because that's constant. So the I will be equal to a third initially into applying this 10 to that value there to the u. So it will become 10 to the 6th power minus, apply the 2 to the u, become 2 to the 6th power. And then I will work that out and I will get the value of my integral if they had limits. So sometimes they give you with limits and sometimes they give you without limits. Well, that is it. You get me? So let me see if I can go back to what original. You understand that, David? You good? Just showing
Yes,
what
sir.
it would be if you had limits, right? If you had limits. All right, so let me just erase all of this because it's not a question. All right, so that's 2022. Let's see if there's any on 2021. Right, I think there are a couple nice ones that exist. But let's see. Let's see 2021 integration by substitution method. Somebody said I wanted some of this as well, but can do this another time. Solving first order differential equation where the variables are separable. Right. See if there's any substitution and integration there. All right, so here's one very similar substitution method. Again, if you look at it closely, when I differentiate the expression inside here, it becomes 3x squared. And 3x squared exists out here. So the substitution really to make is u equal the expression inside there, u equals x cubed plus 4. That is a substitution to make. And they have told us to make it. See? So even if they did not tell you to use, that's what that is what. There are some questions that says use an appropriate substitution. Not all of them tell you what substitution to use. But this one is very similar to the one that we just did. Very similar, just different function, different values. So same thing. By the substitution, u equals x cubed plus 4, which is the expression within. And then differentiate this side, you get du equal differentiate this side, you get 3x squared dx. So the 3x squared dx is already there. See? 3x squared dx, 3x squared dx can be replaced with the du. And then this inside the bracket here is just u. Right? And so we literally can just proceed and so the integral, let's call it integral I again, becomes equal to the integral. This part of it becomes u to the 4th power. U to the 4th power. So it becomes u to the 4th power. And then the 3x squared dx. 3x squared dx is actually du. So I'm going to put du. And you're finished. Because you got, then you're going to get add 1 to the power divided by the new power, get u to the 5th power over 5. Don't forget the constant of integration. You take this now and replace the u right there. Put back the u. Right? So your integral is going to become x cubed plus 4 over 5 plus c. I think there's another more interesting one on one of the papers, and see if I find it. Integration by substitution. Let's look at 2019. 2019. I didn't check it for that one. Probably not. All right, here's one. Again, similar kind of thing, but this one a little bit different, right? Because why is it different? Because if you look at it, differentiate with what's inside here, I'm all get a -1. But I have X out here, so this one is going to be a little bit different. All right, but you still have to just work with what they get. They tell you what substitution to use, so you have to just work with what they give you to use. So for this one, we're going to see that the u is 1 minus x. I'm going to differentiate this side. We're going to 1 du. Differentiate this, you get 0. Differentiate this, you get -1. dx is minus dx. That's what we get. All right. I'm going to make a substitution now. So remember, it is minus dx, that is that, you know. So it means then that I would like to get a minus dx on this. So this integral, I'm going to change it. And put the integral of x times 1 minus x squared. What I'm going to do is introduce a negative on that dx. Negative dx. But I'll put by the minus in front to cancel it. Right? So let me show you. I have the dx here. I can introduce a negative on it like that. Cancel it out back with a negative out here. And then this x will have to be substituted for, because we won't be able to eliminate it. So we're going to see what x is in this equation. And from this equation, you see that the x is also equal to 1 minus u. So we can substitute now. So we're going to replace this x with 1 minus u. Replace this inside the bracket with u. And then replace this minus dx with du. So the integral becomes equal to this minus sign out here first. Times the integral. This x becomes 1 minus u. 1 minus u times the 1 minus x in there is u. So I get u squared. And then the minus dx right here is just du. du. And then what I would do with this now is just expand this out normally. You just have to follow instructions. So I will expand this out normally. I get minus the integral. The u squared times 1 is u squared. And the u squared times u is u cubed. So you're subtracting u cubed. Integrating with respect to u. And just integrate term by term. You can drop this negative inside the bracket now and spin these around. And instead write it as the integral of u cubed minus u squared du. If I drop the negative on this bracket, then this becomes a positive here, and this becomes a negative there. I can integrate now, right? So the integral then becomes u to the 4th power over 4. That's what this one became. Minus this one is u cubed over 3. And don't forget the c, constant c or key. And once I reach there, now I can take the x minus 1 and substitute it back for the u here and there. All right, so my integral then finally becomes 1 minus x to the 4th power over 4 minus 1 minus x cubed over 3 plus c. That's it. All right, Mr. David, think it any clearer?
Yes, sir.
All right, I think let's look at 2018 and 27. Let's see if we can find one more. I think there's a nice, interesting one. There's a nice, interesting one that had some indices in the power, and I have to do some juggling on it. So let me see if I can find that one. But it was another substitution time. I don't remember which year it is on. I don't remember the question. There it is. Yes, this one precisely. So we have to do some juggling with this one. All right, look at it. They give us this to integrate. And this is what they tell us to use. And right now, if you integrate if you differentiate what's inside the bracket, you're only gonna get 4x cubed. The term out here is actually 4x to the 7th power. So we're gonna have to split that up to get the 4x cubed out of it. So let's look at it. It works out itself. So first, we're gonna make the substitution. U equals that. Right? So we're gonna make the substitution. U equals x to the 4th power plus 2. We're gonna differentiate this side. It becomes 1 du, which is just du, equal differentiate this side. When I differentiate this, I'm gonna get 4x cubed. This gone, differential constant is 0, we have to multiply it by dx. So I would like to have this in there, but there's a x to the 7th there. I would like it to be x cubed. So I'm gonna go now and start my process. So this, I'm gonna call it I as usual. So it's almost like a copy the same question and just change the values. So the I becomes equal to, I'm gonna split this up. So I'm gonna get the integral of x to the 4th power plus 2 cubed. This, I need to leave the 4x squared in it. But this is x to the 7th power. So I have to take out the x to the 4th power out of this. And I'm left with the 4x cubed and this dx. So this right here, I've generated my du. That is my du. Understand that?
Yes, sir.
All right.
Yeah.
Now you see this x to the 4th power is x to the 4th power there now. From this equation right here, the x to the 4th power is actually u minus 2. So therefore, I know I can substitute what I can substitute for. I can substitute for this with this. I can substitute for this with this. And I can substitute for this with this. That's equal to that. So everything I can substitute for. So I'm ready to substitute now. All right. All right, so let's go. So I'm ready to integrate now. Substitute first and then integrate. So the integral becomes equal to integral. Now as I said, no, this inside here is just a u. So I get u cubed. And then the x to the 4th is this, u minus 2. So I'm going to put bracket u minus 2. And then this expression here is just your du. That's what it is, du. So this then just becomes du. I'll say expand this out in separate terms now. And so the integral becomes u to the 4th power minus 2u cubed du. I'm integrating term by term now. Right? So the integral equals u to the 5th power over 5. I'm gonna add 1 to the power of that. I'm gonna get 4. So get minus 2 u to the 4th power over 4. Don't forget your c or k. Then it's a matter now of taking this and substituting back for the u here and there. All right. So first one is here, and next one is there, for the u. All right. So substituting for the u now. So your integral result is x to the 4th power plus 2. That's this one. Raised to the power of 5 divided by 5 minus. Now this becomes a half, or it becomes u to the 4th power over 2. So when I write it as that, put the 2 under here, and then u to the 4 becomes this to the 4th power, which is now x squared plus 2 raised to the power of 4 plus c coming right here. That's it. All right, Mr. David.
Yes, sir.
All right. Anybody else want another topic? Just need to go and practice some of the other ones now, David.
Sir,
Anybody else?
remember what year is what?
Sir, the trigs. The trigs.
You want tricks? You know which one of the tricks you want?
What is that, sir?
You know which kind of trick? Well, I'm here a testimony. So where's the testimony?
Sir, remember the first question that I asked you on the 2013 paper? Question 4D?
Question 4D on the 2013.
Yeah, I think it's
Oh, that was
2013.
it's 2014. 2013. I'm coming to the tricks. Maybe we need to spend a whole day on tricks. But we don't have a whole day, but a lengthy period on tricks. Because I don't know why you guys, so the main reason why you guys have problem with tricks, or this one. The main reason why you guys have problem with tricks, is that you don't know the identities, I'm telling them. That's a primary reason. You still don't know the identities as you should. That is the primary reason why you guys have problems with tricks. Tricks is very easy because it presents with multiple ways of solving the same question. That's the beauty about tricks, A lot of the times it can be done multiple ways. If I do the same tricks question 5 times, chances are I'll do it 5 different ways. Some of them. All right, so this one, if you want us to do this, parametric equations, right? It says show that the Cartesian equation of a curve has parametric equation. This is this. It's very easy, You basically are substituting for the t in a mom. So you get an equation with none of the t in it. You basically are substituting for the t. That's how they're doing now. You have these two.
Oh, okay, sir.
And you want to get this. You substitute for the t. So make t the subject of this one and substitute another one there. Look.
Yes, sir. Sir, I just see it a while ago.
Yeah. Easy, man. All right. So no bother then. All right. Which tricks question you want, my boss? Which trick question you want?
Sir, the one where basically you prove, say, one something equal the next.
Or the proofs?
Yes, sir.
So you say the same thing. You have to know the identities. They're very easy, But the first key is to know the identities like the back of your hand. All right? That is the key. All right, we're going to start at 2022 again. Let's see what is on it. The most recent one in this device. 2023 is in the device too, All right, the trick proof we're looking for, right? Trick proof. So you just want the proof ones, right? Trick proofs. All right, this one.
Yes,
that
sir.
one. Okay, man. Them something like easy like cheese, It's an odd maths, Let me show you. Let me show you a couple key things that you need to remember to do them proof, right? Key things. God is never have a second cut and so forth. It's a straight C-sec odd maths proof this now, right? But look on some things we have to recognize. Let me write them out for you. You have to recognize things like this. It's because sine squared theta is 1 minus cos squared theta. You have to realize that this 1 minus cos squared theta is the same as 1 minus cos theta times 1 plus cos theta. So you see that 1 minus cos theta right there, so I am seeing it as one of the factors of sine squared. That's what it is. It's one of the factors of sine squared right now. Right? You have to see those things. Also, because for the sine as for cos as well, the cos squared theta, because it is equal to 1 minus sine squared theta. This is the difference of two squares. So it's anytime I say 1 minus sine theta or 1 plus sine theta, then I know that these are factors of cos squared. So I'm looking to use them. Looking to use them. Give you some general hints again now. Generally speaking, when you're doing a proof, you don't work with tan, sine, and cos all at the same time. What I would want to do with this one is firstly move that tan. Tan is sine over cos. As you work, you're keeping an eye on this. You get me? You're keeping an eye on this. Remember what I've said, you know? This is a factor of sine squared theta. See that so? So sine squared theta, yeah, it equals this time this. Right now you have a factor of sine squared theta, so I'm looking to use sine squared theta there. Right? It's a factor of sine squared theta. Next thing, as I said, you don't work with tan, sine, and cos. You tend to work with tan by itself, sine and cos together. All right? All right. So remember this. Remember this. All right? Very, very important to remember those. All right, let me leave it on the screen. Let me leave it on the screen. Let me leave it there. This time is this one that is relevant, the top one, because of the 1 minus cos. See it here. Now watch this now. First thing I'm gonna do is say, okay, the left-hand side, I don't want this tan. When I look at my answer, I see a cos under there. So you see that tan here, I'm gonna write it as sine over cos. So I'm gonna write back this whole thing. I'm gonna keep back this as is. See there? Sine theta over 1 minus cos theta. See that tan here, so? Okay, no, that tan here, so. I'm just underline it. I'll write it as sine theta over cos theta. This is tan, you know? Sine over cos. That is it. This tan theta is this sine theta over cos theta that I've written. Why did I do that? Because I can pull it off here, so you know, and put it beside it, you know, put tan theta beside it, you know, like that, you know. And I can make it as 2 fractions, sine theta over cos theta times this. So you can break like that. And we multiply a fraction by a fraction, multiply the numerator, and therefore you have to know that it can break like this that I have here now. So this is the tan, this is the tan. What is this up here? That's sine squared. Sine squared has this as a factor in it. We'll bracket up this. Bracket this now then. Bracket that. This up here is sine times sine, which is sine squared. And sine squared can be factorized. See here, sine squared is this. That has this factor in it that will be eliminated. The numerator right now is sine squared, and sine squared is equal to this. So instead of writing the sine squared up here, I'm just going to write this for the sine squared up here. I can leave this on my screen, right? On a paper, this thing. I can leave it on the paper. So this then becomes the sine squared up here. I'm going to write it as this: 1 minus cos theta and 1 plus cos theta all over cos theta times 1 minus cos theta. See, that's what this is. The sine squared is equal to this. Because this is really sine squared. And then these cancel each other. See? This and this cancel. So now I'm left with this over that. Right out here. 1 plus cos theta all over cos theta. See, this have separated them. So when you divide this by the cos theta and divide the cos theta by cos theta. So it becomes equal to 1 over cos theta plus cos theta over cos theta is 1. Is 1 plus 1. 1 And this is the same thing, just turn the other way around. The same as 1 plus 1 over cos theta, which is the right hand side. You done. But the key thing is to know stuff like this, know stuff like that. Understand, very easy. Alright? That is 2022 proof. You know proof? So deal with the proof them, right? Let's deal with the proofs. I'm going to look at 2021 if there's any proof on it. 2021. What just put me to what going on? I don't know why I'm opening up so many of these worksheets. Can just go back and find 2021. I just want one a while ago. Where are you? 2021. See it here. All right. So when I look for a trades, if there's any proof on this now, right? Let's be the other way. Let's come before, right? Come before, yeah, before. Trades. No, I come on after. Welcome. What's the trades here? Trades. No proof on this one. Nah, there's no proof on this one. So I'm proof on it. The question was a stupid question. So this one. All right, there's no proof on that. So look at 2020. I just look right through because I've said the paper weird sometimes, you know. Weird sometimes. Questions all over the place. Let's look through. All right, looks like there's none on this paper, no proof. All right, to see my idea still, let's show you something quick.
Yes, sir.
The question like this now, it's a nice parametric equations question. They wanted to get the dy by dx, right? So I differentiate this side, I get dx equals, when I differentiate cos, I get minus sine, right? I get minus 5 sine theta d theta. And that's this one. This one give it this. And then when I differentiate this one, you will get dy. If I differentiate y, I get dy equals, when I differentiate sine, I get cos, I get 2 cos theta d theta. And you're trying to find dy by dx. So dy by dx will be equal to this one on top here, or this one on the bottom here. So you put in the dy, which is this, 2 cos theta d theta over the dx, which is this one, minus 5 sine theta d theta. And then the d thetas cancel each other. This cancel that. And so this becomes equal to negative 2/5. Now cos over sine is cot. So you could write cot of theta. That is it. But I really want to see if they asked for the Cartesian equation. No, they didn't. But let me show you still if they did. The Cartesian equation like the one with the parameter a while ago. So if they give you these, that use trigger identities. So if you have x equals 5 cos theta, you have to make cos theta the subject and write cos theta equals x over 5. Divide the 5 under here. And if they have the second one, which is y equals 2 sine theta, again, they want to make sine theta the subject, divided 2 under here. And so sine theta would be y over 2. Then how do I eliminate these now? I use the identity that says sine squared theta plus cos squared theta is actually equal to 1. That's it. Square this and put it here so for that. So it will become y over 2 squared plus square this one and put it for that. And that will be x over 5 squared equals 1. And this will be a Cartesian equation Just like that. Right?
Sir, there's a question like that on the 2014 paper. Yeah, I think so. Where they give you a C1. Yeah, I think it's a 2014 paper.
I don't want to digress from the trick proof, what 2014. We're doing the trick proof, right? 2014. I didn't open my 2014 yet. Oh, my 2014 yet. 2014. So 2014. When you say which one?
Sir, I could scroll on. I believe it's 2014 or 2015. Scroll on. Look like it's 2015. Scroll on, sir. Scroll down.
Don't pass those now.
Yeah, yes, sir. It's 2015, not 2014.
This one, no, see there. This attack, see there. But this one even easier. See there.
I was talking about another one, not that, but that also.
All right, 2015.
Yes, sir, in 2015.
This is last question. 2015. You mean like here? This one?
Yes, sir. Question 4.
All right. This one says, give us those two. I said, determine Cartesian equation of C1 and C2. And I want them in this format. Let me split the screen. All right, so we have these two, the same thing again, you know. So for C1, a circle 1, this equation first, I'm gonna make, right, because this is root cos and root cos, I can make those a subject. So for the circle 1, the root 10 cos theta would be equal to x plus 3. I'm gonna square both sides of this, and I get 10 cos squared theta equals x plus 3 squared. And then the second equation is this one. So it would then, if I make this a subject, it would be root 10 sine theta equals y minus 2. I will square both sides, then I will get 10 sine squared theta equals y minus 2 squared. But now remember this now. Remember this now. That cos squared theta plus sine squared theta is equal to 1, you know. So multiply this by 10, then I get 10 cos squared theta plus 10 sine squared theta is equal to 10. So this I can replace here with this. So this can come here, so. Similarly, this can come here, so. And so I will end up getting that the x plus 3 squared plus this one now, which is the y minus 2 squared, is equal to 10. That's it. That's the equation of a circle. And it's in the format. All I need to do is take this 10, square root it, and square it back to get it to the r squared. And the second equation, the second circle 2, we're doing a similar thing. So this one even more straightforward, well, not more, but same thing. So for this one, for circle 2, for circle C2, I would make cos theta my subject first, and so cos theta, no, not cos theta, 4 cos theta. 4 cos theta. Why am I doing that? Because this is also a multiple of 4. So 4 cos theta would be equal to x minus 3. And we'll square both sides and we'll get 16 cos squared theta equals x minus 3 squared. The second equation now is this one. Again, I want to make 4 sine theta the subject here. So 4 sine theta would have been y minus 2. I want to square both sides again. I get 16 sine squared theta equals y minus 2 squared. And then now we go back to the same thing again that we had before, which is that cos squared theta plus sine squared theta is equal to 1. But these have 16. So let's say multiply this by 16. So I will get 16 cos squared theta plus 16 sine squared theta is now equal to 16. Then I can take this and replace this, and take this and replace that. So I will end up getting, first one is x minus 3 squared plus this one now, y minus 2 squared equals this radius squared, this 16, which is same as 4 squared. That will be it. Here's a final point of intersection of 2, but that's for a different topic. Let's get back to the proof.
Sir,
What?
sir, how would you find the point of intersection? You would expand it out and find
What you do, you expand the two circles out into separate terms. Expand this and expand this out into separate terms first. Expand them out into the general form that has the x squared plus the y squared in them, right? Two of them.
Yes, sir. Yes, sir.
Expand the 1 and 2 with the x squared plus the y squared in them, right? And then you subtract them. No, you subtract. You're solving them simultaneously. So the first thing you do is expand them out into separate terms. And then you subtract them. When you subtract them, you eliminate the squared values. You're gonna get the equation of a line. Can we expand them out into separate terms, right? And you subtract them. So it's like you have these two circles and intersect there. When you expand them out into separate terms and you subtract them, you end up with a line equation. That line equation is this line. The line of intersection of the two of them. It passes through these 2 points. Then after you subtract them and get that line, they said you saw the line on one of them simultaneously. You saw the line and one of the circles simultaneously, and that will take you down to the 2 points there. So remember, to solve the simultaneous equation of 2 circles, expand them out in the general form first. This is called the standard form. You want them in the general form with the x squared and the y squared terms in them, both of them. Then you subtract the 2 equations to eliminate the x squared and the y squared terms. You're going to end up with the equation of a line. Then you go further now and you solve simultaneously the line and one of the circles. And that will give you the 2 points. That will then give you the 2 points. But we could do a couple more of the trig proofs, and then we can call it a day until tomorrow. I think what I'm gonna do is try to see if we can start earlier tomorrow. What time you guys are available to start tomorrow? What's the earliest time you can start tomorrow?
9.
9 in the morning. I have to go working on my boss. Talking about in the afternoon, man.
Oh, sorry. Like, well, 4 then.
Yeah. All right. Try for 4, maybe a little earlier. We'll try. I'll send a message and let you know. All right. So we could go back and say, like 28. Let's do a couple more of the proofs and we'll call it a night. I kind of feel tired. See so much stress me out. It's not really that, you know, I was late at work, very late last night till about 2 o'clock, and then I had to get up early this morning because today was CSET day. So I'm kind of tired right now. All right, 2018. See if there's any proof on this one. All right, the proof would have come before the integration. Oh, so we're in truth already and there was none, right? That's what I said. All right, there's one. All right, here's one. Here's one. That looks like a nice proof. But see, before I even start to do this proof, what you have to realize, see, is that, you see this? This is actually 1 over cos 2 theta. And this is sine 2 theta over cos 2 theta. So the right side really is 1 plus sine 2 theta all over cos 2 theta. That's what this side really is, So I will take this side and work towards that. And when we reach that, we reach this. That's why you have to know the thing, like, that way. The right side is really this. That's what this is really, that is really that. So in working towards this, you go work towards that first. And then from that, now, I will get this. And that's what I'm saying. So sometimes you look what the right side is in another form, until we can't see what it is there. Whereas this side is really this. Right? Because this is this, and this is that. And then because I'm of the same denominator of cos 2 theta, then it is really that. So then this is just a matter of taking from this and working to that. All right? All right. Let me see now. All right. So, it's the cos double angle. It's the most powerful double angle. Okay, I can bring it in 3 ways. All right? So what I would do initially to start with this one is try to eliminate the 1 and the minus 1 to begin with. All right. I'm just looking at it to see what approach I would use to begin with, right? Just looking at it first to see. Now sometimes you kind of look at it and see a couple steps down the road before you start. All right. See a couple steps before you see a couple steps down the road before you start. All right. So all right. So let me tell you my chain of thought. I want to get rid of this 1 and this minus 1. So I'm going to have P-trig expression and deal with it, right? That's the first thing I'm thinking. And also thinking that this double angle is very powerful. It will help me to eliminate the 1s, but I can express in terms of 1. In terms of 1s, right? Now that I'm here, I've recognized, all right, leave that. This will work out itself. All right, so instead of going to this straight, I'm going to go to the ERSA first. All right, so let's see now. So how can I eliminate this 1? I have a minus cos theta here, so. All right, so I have to know that it's a cos 2 theta. It can be written as 1 minus 2 sine squared theta. It can be written as 2 cos squared theta minus 1. Those are 2 ways a cos 2 theta can be written. All right. The thing is that this is a minus cos 2 theta. So I can decide to factorize it, the minus from it, and put it with a 1 here. So let me show you what I'm talking about now. So the left-hand side, I can write it as the numerator. I can write it as sine 2 theta. I'm going to eventually expand this, I'm just trying to eliminate the 1s first. I'm going to factorize a minus out of these 2 terms right here. I'll put minus bracket cos 2 theta minus 1. I factorize a minus 1 out of these two terms, that's what I'm going to get. All right? And then under here, I would have this sine 2 theta in front, put it in front, sine 2 theta. Then I would have plus, and then I have this and this, which is now cos 2 theta minus 1. See that? That's what I have so far, right? Good? So far,
Yes,
so
sir.
good?
Yes, sir. Yes, sir.
Watch this now. I'm working. So I want to get rid of cos 2 theta minus 1. So you see this one that has the 1 in it here. I need to transpose over here. All right, because I want to get the minus 1, cos 2 theta minus 1. So I'm not going to be working with this one. So what I'm going to do is go and use, but I do the other way to, with the minus, where the sine squared come positive. No matter, it work out itself. So what I'm going to do is take this now and recognize that it is the same as cos 2 theta minus 1 is the same as minus 2 sine squared theta. All right, that's what I'm going to be using to get rid of the ones, So this, I'm going to replace it with this, and this, I'm going to replace it with the same thing. So the left-hand side then becomes equal to sine 2 theta. I'm going to expand this now to, if you want to know. Well, let's write this up first. Sine 2 theta minus bracket this thing. I'm going to put negative 2 sine squared theta in there over sine 2 theta plus bracket, I'm putting this in there as well, minus 2 sine squared theta. All right, I'm working with that now. So this now, I'm going to expand this out. It is 2 sine theta cos theta. So I'm going to get 2 sine theta cos theta. Small becomes a plus. So I get plus 2 sine squared theta over, this again is 2 sine theta cos theta. But here I'm going to just get minus 2 sine squared theta. I'm going to factorize 2 sine theta out of everything. Everything can factorize at 2 sine theta. So I'm going to factorize 2 sine theta out of everything. So 2 sine theta into, out of this one, I'm going to be left with cos theta plus sine theta up here, so. Right? Over, if I factorize 2 sine theta as well out of this, I'm going to get cos theta again. But this time is minus sine theta. So these cancel. What a question easy. And all I'm left with are these. Remember now, I'm trying to get these double angles in them. Double angle here. Right? All right. It's kind of working out itself. Watch this now. So I'm left with cos theta plus sine theta over cos theta minus sine theta. So watch this now. To get this double angle under here, which is cos 2 theta, I have to know that this cos 2 theta under here is really the same as cos squared theta minus sine squared theta. This thing, the same as that. And how can I get it from this? That's the difference of 2 squares. I have to go now and multiply the denominator by the conjugate of this to present the difference of 2 squares that I want. So multiply the denominator by cos theta plus sine theta. Multiply the numerator by the same thing, cos theta plus sine theta. Right? So the denominator now becomes the difference of 2 squares. So the denominator becomes cos squared theta minus sine squared theta. And the numerator now becomes a perfect square. See that? Perfect square becomes that squared. Which then is, what is that? It is cos squared theta, that's the first term squared, then twice the product of the 2 plus 2 sine theta cos theta. So maybe I'm going around about, and the second term squared is plus sine squared theta. Right? Must be. So 2 pages and give for work, you know. So you know, so there's a lot of work needed. Equal, watch this now. So this and this is my 1. See my 1 here, so my 1. See that? That's my 1. And see this 2 sine theta cos theta is my sine 2 theta. See here? My sine 2 theta. So I've gotten it. Cos squared plus sine squared is 1 plus 2 sine theta cos theta is sine 2 theta. Sine 2 theta over, it's a cos squared minus sine squared, there is cos 2 theta. Cos 2 theta. And then now, this divided by this is sec 2 theta. Sec 2 theta. And then the sine theta over the cos theta is tan 2 theta plus tan 2 theta, which is the right hand side. Works like a charm. That is it. But guys, the key thing with this, you have to know your trigger identities. Much marks for it. It's 8 marks for it, and so I know you have to do some work.
Sir, could you please scroll up?
I know you have to do some work. Right? You have to know your trigger identities like the back of your hand. But this question required. And maybe there's an easier way to do it now. I doubt, because it's 8 marks for it and they give a 2 page. So they really expect you to do some work to get it, right? But the key thing is that you have to keep an eye on what you want, what you're working towards. You have to keep an eye on it. And the bottom line, as I always say, you cannot be working and you're working and hoping. You're working towards something, and you have to know your trigger identities. You have to know them. There's no if or but about that. You have to absolutely know the trigger identities. Right? You have to know them like the back of your hand. You get me? Who knows? Maybe there's an easier way to do it, but that is it. Maybe there's an easier way to actually do it, but that is it for now. Maybe I could have changed this and write that sine squared 2 theta plus cos squared 2 theta. Something like that. And generate some factorize and all of that. And nobody take out the 2 theta. Even so I'm gonna try that way there. Try that way there now. And I bet nobody take out the 2 theta then. Since the answer have 2 theta in it. Can I try that way there now? Alright, let me try that way, guys. More maths equals better, man. Let me just try that other way. When we replace the ones, sine squared 2 theta plus cos squared 2 theta. And see what happens. And factorize. What do you think? Try that. Want to try it? Want to try it?
Yes, sir. Go ahead.
Alright, we could try it. So I'm going to take these off now, right? Alright, let me make one. But I'm not going to write it back, you know. Alright, I'm going to copy this. So if anything I can. But I have the solution on this paper. It doesn't really matter. That's not really matter. I'm going to copy it already. I'll just try it another way. If I don't eliminate the one, but write the ones as sine squared plus cos squared. And keep the 2 theta in there and see if something can work out. Let's see. That's what it goes. Something you have to test yourself, you know. So the left hand side is, I'm going to replace this with sine squared plus cos squared. So I'm going to have sine 2 theta minus cos 2 theta plus, instead of 1 here, I'm going to write as sine squared 2 theta plus cos squared 2 theta. Sine squared 2 theta plus cos squared 2 theta. So actually making it more complicated. That's what this one is. And then under here now, I'm going to put this in front because it is in front at the top. I'm going to put it in front at the bottom as well. So I'm going to write about this first. So I'm going to write sine 2 theta and then they plus this plus cos 2 theta. Then this number because it's a minus. I forgot minus the sine squared and minus the cos squared because it's a minus 1. So I'm going to have minus sine squared 2 theta and minus cos squared 2 theta. Because a minus 1. Alright? I'm going to try to factorize now. So I'm going to factorize the sine and then factorize the cos and see if we get some common factors going. Let's factorize this first, the sine. Not gonna work, you know. It's not gonna work. So factorize the sine 2 theta. Alright. I'm gonna factorize the sine 2 theta. I'm gonna get sine squared plus 1. So no, I get sine plus 1, right? So I get sine 2 theta plus 1. It's not gonna work. Not gonna work. It has become more complicated. It's not gonna work. I'm gonna factorize the cos 2 theta. I'm gonna get cos 2 theta plus 1. No, minus 1. Minus 1. Minus 1. All over. The same thing on the denominator. Factorize sine 2 theta. Sine 2 theta. That's this one and this one. This time I would get 1 minus sine 2 theta. That's this and this. I'm going to factorize cos 2 theta. I will get this and that. So I will get 1 and minus cos 2 theta. Man, in our work here, man. I give me too much things. I really work out. I get me now sit on similar. First way the better way. And normally that's what it is. You normally want to get rid of them. Rather than build on them, you get rid of them. The way that we did it before. Forget about this. Forget about this. No bother. Forget about that. Forget about that. Forget about that. Forget about that. It's not working out. All right, I could do another one. Finish off in a couple of minutes. And I have exam tomorrow. I said, no. And I have exam tomorrow?
No, sir.
All right. All right, so we'll work it through, right? And this is on the video here that I'm doing, so you can go back and look at it. All right, this is what, 2018. We could look at 2017. We could look at 2017 if there is any. It's fun there. 2017. Enter over to 2017 here. All right, truth proof. Now this one. Once this one done, this one straightforward.
Yes, sir. Do it, sir.
All right. So you're going to have to use the compound angles to do it, right? Because it's a proof that you're supposed to know in your head. What I'm asking you to prove it. It's an identity you should know in your head. We're asking you to prove it, right? So you're going to say the left side is tan, which is sine over cos. So it's really sine of A plus B over the cos of A plus B. And you're going to expand this compound angle up here. When you expand the sine compound angle, you get sine cos cos sine. So you're going to get sine of A, cos of B, Since you have a plus, you're going to get a plus and expansion of a sine. So sine, cos, sine. So you're going to get cos of A, sine of B, sine, cos, sine. And the AB following the same order, AB, AB. Then on the denominator, the expansion of the cos compound angle is cos, sine, cos. And this is a plus, you get a minus in between for the expansion of cos. Minus sine, sine A, sine B. Then once you reach it, so now you can have to be smart, right? And what can I be smart? I see a 1 right here, so that is in this position. So to get a 1 right here, it means that I have to divide by cos A, cos B. So what I do, I divide the numerator and the denominator by cos A, cos B. That's all I need to do. Right? So I'm going to divide the numerator by cos A, cos B, and divide the denominator by the same thing, cos A, cos B. Because I want this to become a 1, as I see it there. This is all I know. So what do I get? This becomes equal to this one first. I'm dividing this by this. So I'm going to get sine A, sine B over cos A, cos B. If you want to show this in a red so you can see it, that's what I've divided. All right. Putting back this whole thing. That's this line right there. All right. And I'm dividing this now by the same thing, cos A, cos B. So I have cos A sine B, and I'm putting that on top of cos A, cos B. Let's put about this line in blue. That's this one I've divided by that. After the denominator with the same thing. So on the denominator, this divided by itself is 1. So we get 1 minus this over that. That's sine A, sine B over this thing. Cos A, cos B. Cos A, cos B. You must see it now. This becomes equal to. Now, if you got this, sine A over the cos A is tan A. Right? What's happening here? What am I supposed to get? I'm supposed to get tan A. So make a mistake, you know. See this? It's supposed to be a cos B. Cos B. Not sine B. It's supposed to be a cos B. And they cancel. This cancel in purple. This and this cancel. So this and this cancel. Something cancel by here, so you know. Cos A and cos A cancel there as well. So this cos A cancels this cos A. Alright. So what you find happening then, let's go back for this now, is that this sine A over this cos A is tan A. This plus comes back as a plus. This sine B over cos B is tan B. All over. This is a 1 minus. Now this one now. Sine A over cos A is tan A. And the sine B over cos B is tan B. And that is the right hand side. That is it. See that?
Yes, sir. Yes, sir.
Anyway, I'm gonna break now, you know, guys. I'm really out of it. So better me break, refresh myself, and come back energetic tomorrow. Okay, and push through. So we can get some quality work done this week. Tomorrow and Wednesday and Thursday. I have to be working with the admin students as well. So we have to push through. I have to do some work. The admin students have exam this week as well. The day before. Yeah, I don't know what they've set up this week, but I have to just work it out. So I think we have to go maybe sacrifice. I have to go now whole day Wednesday. Go now whole day Wednesday. So maybe give thing that whole day Wednesday, add mass a whole day Wednesday. And give pure mass a whole day Thursday. Something like that. You guys have exam Wednesday, sir, right?
Yes, sir. No exam Wednesday.
Right. So your next exam is the maths?
Yes, sir.
Oh, okay. All right. All right, okay, see what I can do, yeah? That's what I can do. I've gone some time on this thing, so let's see. But that some people who want something of other subjects as well, like bio Wednesday, I think. So I wanted to give the admin students Wednesday. And maybe give the promo students Thursday. But that's what I can. Maybe we can start earlier tomorrow. And let you know. But keep working in the day. You can message me during the day for anything. That's what you guys need to do. Keep working and just message me during the day while I'm at work, and we can, pop in and do a little hour, like half hour, tomorrow. If you need explanation on something, you just let me know during the day. All right? Try to get some work done. All right then.
All right. Yes, sir.
Come on, cool. All right, gonna end it now.